So first of all, just a quick review of where we were last time. Um, so one of the major concept we introduced last time was the EMR, the electromagnetic spectrum. So we know it's a very long and continuous spectrum. We know the visible portion because that's how we can read the different colors, the visible portion. But also, there are some other portions that are also very useful in remote sensing, the ultraviolet, infrared. So in infrared, there can be near infrared, mid-infrared and far infrared, and also thermal infrared is part of the infrared portion. And also in remote sensing, we also use microwave, which has which has great penetration power and which can help you see through the cloud cover and just see what's underground. So basically, in this class, we'll introduce the different image sources and the major applications, and also you will get the chance to play around with the different types of images. And also, like we said last time, you are not expected to remember the wavelengths portion, like, for example, from 0.4 to 0.7 is which portion. But I do want you to be able to say, when people talk about infrared, infrared is in this relatively longer wavelengths portion compared to visible, and microwave is the longest wavelengths. So, those are the things I think you will naturally memorize as we introduce more different sources, but also you can try to take some quick notes to remind yourself. And another important concept we talked about last time was the spectral signature, which is also the, basically like the fingerprint of the different ground covers. And because of, the different ground covers have a very different typical spectral signature with a spectral plus, we're able to distinguish them image. We're able to classify the image. We're able to produce a very detailed land use and land cover map. And here I'm showing a different example, actually from a different source. In the first lab, you did Iconos, which has 4 bands. So your signature plus will only basically have 4 nodes. But in my case, I have 6 spectral bands in total, and that's why I have a little bit more details. And today we're going to introduce some other sources. Basically depends on the number of bands a particular sensor has. You will be able to see different level of details. And on the Y, so for the spectral signature, what is plotted on the Y-axis is known as the spectral reflectance. And also just a quick reminder about the energy interactions. So reflectance, is basically measured as the ratio of reflected energy and the overall incident energy, which is definitely less than 1. So, it's essentially the ratio, and the value is between 0 and 1. The higher the value, the higher the reflectance. So essentially, we use reflectance to kind of like measure or quantify, the variations, and based on reflectance, and also based on essentially your pixel values, you're able to produce the spectral signature, and you're able to distinguish between different ground covers. And also, in addition to the reflected energy, some energy may be absorbed, transmitted, and the absorbed energy could be emitted later, for example, as a form of thermal energy. So, because of this complex interactions, it enables us to measure and to quantify images across the different bands, and with information across the different bands, we can see this is a vegetation cover, and here's a farmland, and maybe it's a water body or some buildings and pavements. And for today, just a quick review. Today we're going to talk about some kind of related but also more specific concepts on the sensors and images. And today's topic is multispectral, thermal, and hyperspectral remote sensing. And also, the biggest slide I have here, we're going to spend most of the time today to talk about image resolution. And for image data, there are 4 types of resolutions: spatial, spectral, radiometric, and temporal. So today we're going to focus on the 4 types of resolutions, and also Actually, the multispectral thermal and hyperspectral, they're related to one of the resolutions, spectral resolutions. But also, more importantly, what is interesting is the 4 types of resolutions. First of all, they kind of together, they define an image. Each image from any sensors, they must have a certain spatial, spectral, radiometric, or temporal resolutions. And those are actually the 4 types of resolutions are your criteria when you select your data. Given that, for example, maybe you have access to 3 different data sources and you're trying to pick one for your research, for your project, and you have to evaluate their spatial, spectral, radiometric, and temporal resolution and see which image source works the best. And also today we're going to talk about how the 4 types of resolutions, they trade off. Actually they're not only, they're not independent. They kind of like work together where they determine each other, where one resolution could actually refrain another one. So it's just all depends on the technological limit we have, and also which determines the data. You can say quality, but it's more like the characteristics of your data. And also along the way, because as today we're also just talking about the basics of image data and of sensors. So here's what we're going to do today. So I'll be basically going over the lectures and giving you folks examples, and I may pop up questions for you to answer, which you may respond in the chat, or unmute yourself, or maybe use your annotate. And also, by the way, I guess some of you are new to Zoom, so you should be able to see an annotate button. So if you click on annotate, you can draw, or you can you can label, or you can. I have the spotlight option, but I don't think you will. So the spotlight, I believe, is only available to the person who is sharing a screen. So feel free to annotate as we go. But there's one thing I want you folks to do today. Since we're going to introduce some relatively new concepts today, so I want you to, as we go, everyone will write at least one multiple choice question based on what we cover, and you can send it to the chat. I hope this makes sense. So basically as we go, you probably can, I'm sure, because I'm sure you have taken many different tests so far and have done so many different multiple choice questions. So I'm pretty sure you will give me very good questions. So what I'm looking for is, as we go, if you kind of capture something very important or tricky, you will just turn that into a multiple choice question and then send it to the chat. And you don't have to wait until the end to do so. So whenever you see appropriate, or whenever you see something interesting, you can just send it to the chat, and I'll be sure to stop and go over the questions you have. And also, of course, you can just give something more like definition based. But I think it will be more helpful if you can, focus on just basically create something trickier. So more than just a definition, like what is this, what is that, but more about maybe combining the different resolutions together. And also we're talking about multiple choice question, but also feel free to do a true or false, or maybe you feel like it's a very good fill in the blank question, or some other forms of question. Feel free to do so. And we'll just stop in the middle and then look at your questions as a way to review. And also I think hopefully that way you can bring up some questions and we can talk about your questions and as well. And try to be adventurous, which means you may not really sure about the question, but feel free to bring it up, because the point is we are going to talk about it together. Okay, so let's get started with image resolution. And like I mentioned earlier, there are 4 types of resolutions for image data: spatial, spectral, radiometric, and temporal. I will give you examples. We'll go over each. But also, I felt like for, among the 4 concepts, you should find some of the concept really familiar. For example, spatial, because as long as you have seen image data, you probably have some sense of what the spatial resolution means. And also, even if you don't know the term of radiometric, when I show you an example, I'm sure you will be able to see what that means. So the only thing I can see that is relatively new, maybe the spectral, but also it's ongoing. So we're talking about the spectral resolution, the spectral information the whole time. So yeah, let's get started with actually spectral first. And also before that, I also want to point out that, last time we did a lab, and many of you had some questions, and which were all pretty good questions, asking about are all images are going to have only 4 bands? Are the band 1 always going to be blue? The answer is no, because the different sensors, all real sensors, they have a fixed limit in terms of the 4 types of resolutions. And also, the point is the different sensors, they offer different resolutions, which will basically give us options to choose from. Otherwise, if they all have the same spatial, spectral, radiometric, and temporal resolution, that means we don't really have options. So the next part is just all the images, all the sensors are different in terms of what they can offer, their capacities in terms of recording images across the 4 resolutions, and that allow us to do things with the different data. So let's first talk about the spectral resolution. So spectral resolution refers to the number and size of spectral bands the sensors can record data in. So which means, just think about a sensor. A sensor may record data in only 1 band, or multiple bands, or many, many, many different bands. So by category, we just classify spectral resolution to be 3 general categories, but also more specifically, you should refer to the spectral resolution of a sensor to say, for example, this sensor has 4 bands. So we're talking about ICONUS. We know there are 4 bands of ICONUS, and also you should be talking about, for example, band 1 is blue, band 2 is green, band 3 is red, band 4 is near infrared. So we're interested in, whenever we're talking about the spectral resolution, we're interested in both the number, how many bands an image has, and also the size of each. And for the size of each, you can go very specific and say it's 0.4 to 0.5 micrometer, or you can just be really descriptive and say it's blue, it's red, it's green, it's near infrared, it's thermal infrared. So you need both. So let's just go over the 3 categories. The panchromatic sensor, so which is actually, you don't see that very often, but it's very useful. So we'll talk about why the panchromatic sensor can be useful later today, and also 2 weeks from today. So there are some techniques you can apply through the panchromatic sensor. So for panchromatic sensor, it's on a single channel detector, so which means there's a single band. And when you display a panchromatic band, because it's a single band, it's going to be shown as black and white. Of course, it's going to be a grayscale. So black and white, but also the grayscale in between. You don't see colors because there's only 1 band. So your red, green, and blue color guns are only going to show the single band, panchromatic band. And most of the time, you work with multispectral sensors, and the multispectral sensors has multiple bands apparently. So by definition, we say if a sensor has 2 to 15 channels, 2 to 15 bands, we call this sensor as a multispectral sensor. And there are some examples, and now they should be just a name without meanings. But in a few weeks, you will find some of them rather familiar. For example, Landsat is really the most useful image source because it's free, it's global coverage, and also it has a long history of recording data since the 70s. So I'm assuming for most of your final project, you may have to use Landsat. So Landsat is an example of multispectral sensor, and depending on which generation of Landsat you're looking at, You may have 7 bands, you may have 11 bands, and also they're going to launch a new Landsat, new sensor in September this year. That will be Landsat 9. So really you will be seeing a lot of changes going on. And in addition to the multispectral, sometimes you may have hundreds of bands, many bands. And in this case, we call this types of sensors as hyperspectral sensor. So basically the hyperspectral sensor, because they have hundreds of bands, they usually give you a continuous reading of the whole optical spectrum from visible to infrared, and they record tiny little portions, and they record many tiny little portions across the whole range. And one example is the AVI-RIS, and we will introduce another example, which is also available in certain portions of the United States if you're interested in hyperspectral sensor. Just a quick idea, just to make sure that you actually see the true difference among the three. So among the three categories, which one do you think will offer you the most spectral information? Panchromatic, multispectral, or hyperspectral? You feel free to circle, or feel free to just speak up or respond in the chat. Simon, I saw you raise your hand.
I feel like hyper usually means the most.
Yeah, I just circled hyper.
Nice. Yeah, we have some hyper. We have hyper in the chat as well. Yes, hyper will give us more information because it's hyperspectral. It has many different bands. And also, for those of you who are really interested in like species level mapping, for example, vegetation mapping, or like down to the a particular land cover, but you want to just be able to differentiate the very detailed spectral signatures, hyperspectral sensor is your go-to option. So let's spend a little more time to talk about the spectral signatures. So by spectral resolution, the multispectral will give you multiple. So, we know for now, by definition, we say it's 2 to 15, but, it's roughly the case that you have a number of fixed distance band that is just basically each one is measuring a different portion across the EMR spectrum, and will give you the information on the different portions. And also, once again, whenever you're in a display device, you're going to only visualize 3 bands at a time, for the most, because there are only 3 different colors to show the different bands. However, most of the time, like when you do actual analysis, you're going to use all the bands together, which will offer you, for example, if there are 11 bands, the 11 bands altogether can offer you more information than only seeing the 3 bands at a time. And one specific example of the multispectral band, a multispectral sensor is the thermal sensor. Thermal sensor is basically, essentially, as you folks know, I think we talked about the thermal sensor a few times. So basically, you measure the thermal properties. Let me just show you a few examples. And we actually have a question already in the chat. So we'll go over the thermal image examples, and then we'll look at the question. For thermal image, and usually, for example, Landsat has 1 to 2 thermal bands, depending on which Landsat sensor you're looking at. And for the thermal band, it offers you the information in, basically the relative temperature. However, because how the data were stored and recorded, you have to apply some transformations in order to get the temperature information. But essentially, it just gives you a relative sense of it's warmer or it's cooler. So in the first example, we're seeing a urban area. And also here, the yellow color is used to show the higher thermal values. And the purple is used to show the cooler or the lower thermal values. And also, by the way, in Erdas Imagine, or basically in any image analysis program, you're able to change colors the way you like. For example, you can just use black and white, but also you can use yellow to purple, you can use red to blue. So you're free to use any, any color scheme to visualize your data. And specifically, this kind of image in urban area, it's actually, I'm sorry, it's a nighttime image, and will show you the idea of building heat loss. So you can see for the building, the construction area is fairly cool. However, surrounding each building, you'll be seeing this warmer outglow in terms of the pixel values. And with this kind of image, in addition to like using thermal image to analyze the climate-related applications, building heat loss is another application for you to apply thermal image. And the second image, because I know you all have access to the slide, I wouldn't really ask you what we're looking at. So this is an example of, basically water discharge, heated cooling water from a power plant into Lake Michigan. And here we're using the white to show warmer color. And that is usually by convention, we use white color to show higher values, to show warmer areas in terms of thermal band, and use black to show cooler. So that will just also give you just some ideas on thermal image examples. And of course, you wouldn't be just only looking at them. You can quantify, you can analyze, you can measure. And in addition to the two examples here, thermal image can be used for, for example, urban heat island analysis we talked about for climate change if you want to measure temperature. And also some are using the relatively higher resolution thermal image to analyze animal species, because you can see higher emittance and higher thermal properties from the animal individuals. So just some examples, and let me see if I can drag the chat. Okay, great. Okay, so now we have one question. And Simon gave an answer. Let me just read one more. Okay, a panchromatic sensor is a single channel detector to do 5 or hundreds. So we know is by definition, a panchromatic sensor is a single channel. So the answer is A. So keep your questions coming. And we'll keep talking about spectral. So for the hyperspectral sensors, like we mentioned, there are many bands, very narrow, continuous almost. And usually you record data throughout the visible infrared, infrared meaning near infrared, mid infrared, and thermal infrared portions of the spectrum. So let me just show you actually a visualization of the hyperspectral concept. And here, if you could recognize what we're looking at, the one I'm circling out here is an example of the spectral signature from a hyperspectral sensor. So which looks really smooth because we have many nearly like continuous bands. So, it really looks different than the 4-band spectral signature from the Iconis, or like maybe 6 bands from Landsat. When you have 200 bands, you can really see, just monitor how, the details change across the whole portion of your spectral, of your EMR wavelengths. And also in a hyperspectral image, you'll have many different bands, and they come together. So oftentimes, this is referred to as a image cube, because you have a whole range, like over 200 different bands. They are going to put them together to analyze. So in this class, we're actually not going to work with hyperspectral image in the labs, but I will see if it's possible for us to maybe play around with hyperspectral just as a quick hands-on exercise. So the idea is, after you download hyperspectral data, you will have, for example, if there are 250 bands, you will have 250 files in your folder. And the program, Ernest Imagine, would allow you to stack them together and to generate your final image. And also that is to say, the file size is going to be large because basically it comes from a combination of all these 200 files. Okay, so that is about spectral resolution. So even if you may find the concept relatively abstract, but also we'll work with real examples, and you will see how the different bands looks like in the different labs and also in your projects. So hopefully, over time it will make more sense. So for spatial resolution, I felt like that should be a pretty familiar concept. So here I have 3 examples. Which one do you, well, we know it's 2-meter resolution, 8-meter resolution, 16-meter resolution. So which one do you think, or which one do you describe to have the highest spatial resolution?
Two-meter?
I think I heard a 2-meter, and we have a 2-meter in the chat. 2-meter, and Simone has the circle here. Yes, we usually describe the 2-meter as the highest, the highest spatial resolution. And also to just, avoid confusion, because when we say 2-meter has the highest resolution, so basically we see, the lowest number in terms of spatial resolution has the highest resolution. So oftentimes you will see people talk about is finer resolution or is coarser resolution, because that way we know exactly people are talking about fine and coarse. So the spatial resolution, basically measures the dimension of the smallest objects that could be recorded on an image. And also when we say 2-meter, 8-meter, and 16-meter, we're actually talking about one side of the pixel size. So 2-meter is actually 2 by 2, so it's 4 square meters, and 8-meter is actually 8 by 8, 64 square meters. But also by convention, we just talk about one side because the image data, the pixel is usually in the form of a square, unless you distort it or unless you resample it or aggregate to a different level where you change the projection without resampling. So let's also just talk about one related concept to spatial resolution before we look at Daryl's question in. Well, actually, Daryl's question is going a little further, so that is related to the next slide. Nice. So I want to talk about one related concept because this concept can help us better understand how image data were recorded and why some of the resolutions will interact with each other, or they may trade off. So the IFOV refers to the instantaneous field of view. And essentially, what we're looking at, this beta, this angle in the form of a conic angle is referred to as the IFOV, the instantaneous field of view. So basically, that's how your scanner can see the energy or can record the energy within this, this angle. So whenever we're talking about resolution, we're actually referring to the ground portion, the ground resolution element, and it more specifically the diameter of the ground portion within the IFOV. So we call this diameter as the spatial resolution. So that is also to say, for example, if you have a 10 by 10 meter resolution, so that is to say that the diameter is 10 meter, and that is why we can only record with a 10 meter resolution, you can only see, any object that is greater than that is greater than 10 by 10 meter to be recorded, because otherwise anything within your ground element will be aggregated and averaged. For example, even within this 10 by 10 meter, you have maybe some water, some farmland, and some soil. they are going to be aggregated. And also when it comes to the image data, it will be a pixel value, an average pixel value among whatever within this ground resolution element. So we'll just leave the concept here and we'll come back to the idea shortly. So we have 2 more questions. So let's take a look. First, for Derek's question, which of the following is an aspect of the IFOV? Ability to discriminate very slight differences in energy describes the content of the image, angular cone of visibility of the sensor, size of the smallest possible feature that can be detected by a sensor. What do you folks think? I like this. Okay, we have 3 C's. Very good. I believe that's a C, right? Okay, it's very tricky with the D here. Okay, and from Simone, why are clouds unique from water or vegetation in their reflective wavelengths? They're highly reflective in the near infrared wavelengths, and they're highly reflective in the short wave near infrared. And they're highly reflective in the whole visible spectrum. What do you folks think?
I noticed it doesn't really correlate to today's lecture, but
yeah, and also I feel like it could be less specific because you know, in terms of cloud color, yeah, I will look at your answers first. Where is the line? Okay, we have some C. Is the a response to the new question?
Yes.
Yeah, I would go for A, but also maybe a C.
Professor, you have to choose one.
C.
Correct.
I mean, this is, yeah, that's definitely, I think it's kind of related to what we talked about last time, but also more for future. But that's nice. That's actually pretty nice. Okay. Keep your questions coming. So that's a C, but you know, just I think the general idea is because the cloud cover looks pretty white in an image, so that's why I finally decided to go with a C, because if they're highly reflective in the whole visible spectrum, then it's going to be.
Yeah, and then they drop like after 700. They like completely drop.
And that's how some of the longer wavelengths can penetrate through cloud cover. We'll come back to this. So yeah, it's a little beyond. And also just, you know, come back to the FOV. Before we move on, just a quick check. So, so now we know the FOV, you know, kind of determines the resolution of the image. So between a larger angle and a smaller angle, or basically a larger FOV and a smaller FOV, which one do you think can record more energy? Or is easier for which one to record more energy, larger or small IFOV?
Wouldn't a large FOV record more energy but less accurately?
I like that. Yes, larger will be more energy because, you know, just based on common sense, if we just enlarge the angle, there will be more energy coming in. However, like Andrew suggested, basically larger, that would mean the ground portion will get larger. So less accurate or coarser spatial resolution. Okay, so we'll come back to this idea by the end of today. So let's just first move on to talk about radiometric resolution, and keep your questions coming if you have anything, or if you do have something maybe from last time or more general, feel free to do so as well. I hope I made sense for the larger, which one recorded more energy, because I'm just now reading the chat. We had two smaller. That makes sense, like a larger angle will have more energy coming. So it's just, I mean, there's nothing tricky. It's just all about, the physical properties. A larger angle, it's easier for a larger angle to record a more energy because we're looking at a broader area. For radiometric resolution, let's think example. Yeah, it's kind of hard to control the desktop version of my Prezi. I'm sorry about that. So radiometric resolution basically refers to the different level of brightness that an image or a sensor can record data in. So basically here, for example, between the two examples, we can see apparently the bottom example from 0 to 7 can record a higher level of brightness values. So when it comes to the image, just look at the example here. So radiometric resolution basically defines the level of brightness a sensor can record data. And also specifically, we use the unit of bit to quantify radiometric resolution. And also, essentially the 2 bits represents 4 different levels because we're going by the power of 2, and the 3 bits basically means 8 different levels. So the example images here, the first one, 8 bits, basically the 8th power of 2, so that represents 256 brightness levels. And the second example, 2 bits, 4 levels, and the last one is actually a bit extreme. 1 bit represents 2 different brightness levels. So we can really clearly see that how the 8 bits will give you a more detailed image in terms of the level of brightness, because we do have really dark and really bright, but we also have the range of grayscale in between. And for 1 bit, only black and white, nothing in between, because 1 bit image data can only record image in 2 levels. So it's either high or low, either white or black. There's nothing in between. Very simple, but also it doesn't offer you that much information. And actually, ICONUS, if you did lab 1, you probably remembered because you have to record the pixel values manually. And you probably remember your numbers are usually higher than 256. So actually, ICONUS has a radiometric resolution of 11 bits. So that's why you're seeing a much higher value. And also by now, you folks can see how radiometric resolution is related to the idea of the pixel values we have been talking about. So let's also talk about the pixel values. And here I want to introduce 2 related concepts. We know pixel values. When you look at image, when people say pixel values, it's kind of easier for you to see pixel value is a value that a pixel will store. However, in remote sensing, more commonly, you will be seeing people using the term either by digital numbers, DNs, or brightness values, BVs, as opposed to pixel values, because these 2 values, they are better in terms of describing the image properties. So just make sure when people say digital numbers, brightness values, you know that they're talking about the actual pixel values of your image, the individual pixel values. And also, just the idea kind of they work together. We know the sensors usually has a limited storage capacity. So depending on how much they offer, they usually give you a fixed number of bits and to record your data in. So depending on the radiometric resolution, higher or lower, you record different level of brightness values. So right now, most of the image data we work with will be higher than 10 bits. So Landsat the recent Landsat data also has a higher radiometric resolution compared to the older generation of Landsat, and Iconos has 11 bits, and 11 bits is also a very typical radiometric resolution for many commercial satellites. But also, so far, we talk about the 3 types of resolution, and you probably are thinking about, do I have to remember or memorize all the different resolutions for the different image sources? And the answer is also no. I don't expect you to memorize. However, just make sure you check the information before you use any data. For example, actually for today, we have a review assignment. I will be asking you to read the technical document of Landsat 8, and you tell me what are the 4 types of resolution for Landsat 8. They actually give you the information, but you have to read and find the information specifically. So it's more about looking for reference, and also as you use an image many times, you will remember naturally, but you don't have to try to remember right now because it doesn't make sense. You have to use it first. Okay, so radiometric resolution. So basically, it will gives you the idea of how many brightness levels an image can record, and it determines the level of or the range of your digital numbers or brightness values. We have a math question in the chat. Let's just talk about this now. I think I may have to Google. Okay, so from Andrew, how many values would be possible in a 6-bit image? Do we have an answer? $64. So we have we have 2 C's here. So you just do the 6 power of 2, and you will get 64. Oh, and also, by the way, I think that's something you have realized. So the image data, just like other systems of recording information using the bit system, they start with 0 as opposed to 1. So that is to say, for 8-bit, your digital numbers can range from 0 to 255, as opposed to 1 to 2656. And your 11-bit will range from 0 to 2047, and your 6-bit image will range between 0 to 63, because they start with 0 as the beginning number. Next. Keep your questions coming. So now let's take a look at this animation from NASA. NASA's Earth orbiting satellites. It was from 2012, so that's why it doesn't really include some of the newer satellites. But we'll give you an idea of how the Earth orbiting satellites work, or how they run through, their revisit patterns for the whole system. And so far, I felt like you probably couldn't recognize so many of those, but at least for example, the EO1 has a hyperspectral sensor, and that Sat7 is actually running pretty fast. So in 2 weeks, we'll be talking about some of the sensors, and so that you will see how you can use the data. And the one just passed, the Suomi NPP, is an important source of nighttime image. So NASA, they do offer some great image data. But actually the whole point I was trying to show you the video was just to show you the idea of what is a temporal resolution. So, as you folks can see here, we can actually run this again. So essentially each satellite, also, by the way, they may have one sensor, or most of the time they have multiple sensors. So each sensor may do different things. So each satellite, they run through their, following their orbit, and they scan a little portion of the surface of the Earth. And then, by the next round, they will, as also the Earth rotate, they will, scan the next portion, of the Earth's surface. And they just keep this going. You know, for example, they start, so now you see a portion like scanning the surface of Chicago and also any, you know, other locations along the same orbit. And then, you know, for the next round, they may come back and scan, you know, a portion of Lake Michigan. So which means it really takes some time for the same satellite to come back to the same area and record the next image. So we know, you know, one of the major use of remote sensing is to look at the temporal changes. However, you know, sometimes you have to consider how often do you need to use your data. You know, for example, if you're thinking about disaster management, you want to measure before and after, you probably really want to have like daily images, you know, so that you can see the immediate change, and that can be very useful. But also if you're seeing land use and land cover change, you will want to wait for maybe 10 years to really look for the changes in between. And that will relate to the temporal resolution because, you know, different image data, they offer different temporal resolution, and which will be useful for different applications. So temporal resolution, basically, they define the revisit time, the interval, basically the interval in between that you can scan the same area of the Earth's surface. You know, for example, that can be 16 days. Or in some commercial satellites, they can, depending on the latitude, they maybe offer you daily recording of the same area. It all depends on the satellite and depends on whether you're going for a free data source or a commercial data source. And this time interval, this revisit period for for a sensor to revisit the same area, the same portion of the Earth, it's called the temporal resolution. So just you know, one more quick visualization here. You know, basically we define the interval in between. You know, for example, it's 16 days and it's maybe 1 day, whereas you know, a week. And we're almost approaching the end of the slides, so please keep your questions coming as you know, as we talk about the different concepts. And also, by the way, you know, here ideally, you know, for example, some Landsat data has a 16-day temporal resolution, which is really the best they can offer. However, whenever you go to the online database, you know, for example, the Earth Explorer, which is one of the primary database, we download Landsat data and other very good important image data. Oftentimes you will see it's more than 16 days. For example, if you're looking at an image that has a 16-day temporal resolution, you don't necessarily always get, you know, like for example, you get the first one in June the 1st, 2005. You don't necessarily see one in on the 17th, and that is because you know, they don't necessarily push all the data to their online platform. They have to process the data, and also they only push data that is recorded to a certain level or processed to a certain level. So sometimes you may see a jump of a longer time. And also depending on, actually related to Simon's question of cloud cover, which is a common issue with, you know, like tropical regions especially. So if your study area is in the tropical region, and because of the presence of cloud cover, really, you know, sometimes you don't see a useful image in a whole 3 years, you know, because most of them will be covered by heavy cloud. So here is, you know, this idealized scenario that has a certain, you know, temporal resolution with certain time interval, a revisit period. However, in the real world scenario, when we deal with real data, depending on your study area, depending on where you're looking at, the actual case, you know, the real world scenario can be even worse because of, you know, the different challenges like, you know, data quality issues, processing levels, and they do process data before they publish. So depending on which processing level you're looking at, you may see a longer revisit period. And also depending on whether there's cloud cover or not, sometimes it can even be longer. Okay, so actually this will be my final slide. So for those of you who haven't sent your questions, I think it's time to send something. But actually I do have some questions for you. So my first question, based on the 4 types of image resolutions we talked about today, my first question is, can we change the resolution of an image?
Yes.
Can you give an example, Simone?
Okay, maybe not, but I thought like high resolution, depending on what kind of software you have.
Okay, I see what you mean. Yeah. I can see Simone's argument. So she was talking about if you have a high resolution image and you throw that into a program, there are some tools for you to, for example, if you have a 10 by 10 meter resolution image, you can aggregate your data to generate something like 50 by 50 meter resolution. Not a resolution, sorry. And I saw Daryl put a no. So my original idea was a no, because in terms of resolution, that is determined by the sensor's capabilities and how they were designed. So just to be precise, resolution cannot be changed. It's just all determined. And it's also kind of beyond what we can, because that's the engineer's job. They're designing a sensor for a particular type of application. So we don't really see, or we don't really have the option to determine the resolution before we get an image. We just see the options there and we take an image that is good for a particular use. So I would say the answer is no, because image resolution is, is determined or limited by the sensor. However, like Simone said, you can change the actual properties of the image. For example, you can change the pixel size. So let's say it's the pixel size. So the pixel size is not necessarily the spatial resolution. So I'll take a question from Daryl first.
Well, when you do that, aren't you going to run into MALP?
Yes. Yes. So basically, it's not only, so that's definitely one of the issue of, there's a concept we talk about in most JS classes, which is the multiple, the MALP, the
modifiable
multiple
area.
aerial, Andrew.
The modifiable aerial.
Yeah, the multiple, right. Yeah, that's basically like when you change scale, or when you change the zones of data. So in this case, will be when you change scale, you will have a lot. You will just basically lead to a lot of information. That is true, but also sometimes that can be useful. For example, you have the image source that is 30 by 30 in terms of resolution. However, your thermal image is only 60 by 60. So if you want to work to combine both of them in a particular application. So you have to figure out a way to combine 2 image sources with 2 different levels of resolutions. And in that case, you have to resample your image in order to combine them. So that's, again, there will be a lot of information, but in certain cases, that can be useful. Although of course that means you have to downgrade your data from 30 to 30 to 60 to 60, but it can be useful in some cases. And also, by the way, for spectral resolution, I would say it can be resampled. So you can resample your image, or you can determine certain bands you don't need. For example, I'm using Landsat, but in this particular, maybe a project that I don't need thermal image, I may take the thermal image out so that I only focus on the the visible portion and the infrared portion. So you still have the option to kind of resample. So in terms of we couldn't change the resolution, I'm talking about the original resolution limited or determined by the sensor. But you can still resample your data. And temporal resolution, like we said, you can determine the time interval. You can do a 10-year long analysis. And for radiometric resolution, it also can be resampled to change the the different levels. But again, the original resolution stays the same, but you can resample from 8-bit image to a 4-bit image, for example, because sometimes you may deal with data from different sources with different radiometric resolutions, spatial resolutions. Resample can help you. Resample can basically help you merge your data together. And also, once again, MULP stands for Modifiable Error Unit Problem. And my second question, is there an optimal image resolution?
I would say it would depend on what you want to work with. So the optimal would be as long as you can see what you're trying to study for your.
Yeah, I definitely agree. And Daryl basically said the same thing. I think like whenever you're popped with the question of like, is there like a best or is there like an optimal something, you can always say it depends. Because really, I think the answer to this kind of question is usually no, it depends. So in this case, it depends on the research question, your study area, your availability of time, money. For example, if I'm going to do a global scale analysis, even if I have access to a 1 meter resolution data, I probably wouldn't be using the 1 meter resolution because first of all, for a global coverage, I couldn't imagine how many, just basically the file size is a problem, the processing time, and also the level of details will only mess things up. So for a global resolution, oftentimes we see, people using resolution of at least 1 kilometer because you don't need that high level of details and you don't have that much time. So really, remote sensing is something you have to be patient because the image processing time can take forever. I actually talked about an example last week in a graduate level class. There was one time I was doing a research, even just focusing on a metropolitan area, and one procedure of the processing took me 7 hours. And also that 7 hours wasn't like I just run it and go. I have to repeat the 7 hours multiple times until I chose the best one. So really sometimes a remote sensing project can be time consuming. Something I think important to the graduate students to think about. So if you're doing remote sensing projects, you will really want to start early so that just in case some process runs forever, you have the time to get it done. And also maybe you have to arrange your time really nicely so that you don't waste your time.
Does that depend on the hardware you're using, like your computer?
Yes, but also in the 7 hour case, I was using a really nice workstation.
Wow. Okay.
So there's still a limit of I guess maybe say 50 years later, hopefully that shouldn't be a problem. And also actually right now, I briefly mentioned Google Earth Engine, which is a cloud-based image processing platform provided by Google, of course. So they are doing the parallel computing, which is way more faster than desktop-based processing. So that's something we can try later this semester. So you only need to know some simple coding, very readable code, and you can do analysis. And the data, they actually give you the data source, so you never need to download any data. Your computer is completely clean and it's saved on your account. You can clip image, you can combine image together, you can run some of the analysis from their libraries. So we'll talk about some of these new possibilities which can be very useful. That will happen later this semester once we are pretty much done with ERDA's Imagine and learn the basic functions. Do we have any more questions? And also another explanation of why we don't have like an optimal image resolution. So, I assume sometimes like whenever we're talking about optimal, well, I think you might be thinking about something really high, like high-end spectral, high-end spatial, high-end radiometric. ideally like very high resolution across the board. But the problem is the different types of resolutions, they trade off. So which means there's no way that you can have the highest of everything because it's just not possible. Let's take a look at the example here. So I'm using the Iconos data again as an example because so far we have been using only Iconos. There are 4 bands for the multispectral image that I gave you in the lab. So we know it has blue, green, red, and near infrared. In the resolution specifically is 3.2 meter. However, in addition to the multispectral band, the 4 bands, Iconos also has a panchromatic detector, which will give you one more layer of information. But if you look closely, what is different here? The spatial resolution. I mean, I don't know if you folks can see because, you know, the black and white image probably doesn't look as closely. And also, you know, since I was taking screen captures, there could be a lot of information as my computer or as Prezi compress the image. But I promise the panchromatic Iconos image has a 0.8 meter resolution. So panchromatic band has a higher spatial resolution. However, the multispectral bands has a coarser resolution, although they're both pretty high compared to other low resolution or moderate resolution image data. And this is usually the case. So for example, Landsat has panchromatic bands, which is 15 meter by 15 meter resolution. However, their multispectral bands are 30 by 30. And their thermal bands are actually 60 by 60 or even 120 by 120 meter. And this is always true. And this has to do with the FOV concept we talked about earlier, the instantaneous field of view. Because for a high spatial resolution data, you have to use a smaller angle to record a smaller element on the ground. But the smaller angle, which means you will record less signal and more noise. So basically, there's not enough signal for the image to form good quality. So in order to compensate the loss of information, you have to broaden the spectral window so that you can receive more energy from this smaller spatial angle, if that makes sense. So that's kind of how the trade-off, a simple example of the trade-off between the spatial and spectral resolution. If you want to use a smaller angle, a higher spatial resolution, a smaller ground portion, there will be less energy, and then you have to just not enough spatial. Let's get more spectral. So a broader spectral band. So basically, the panchromatic, as you folks can see, it just covers the whole spectral range in order to receive more energy to make this panchromatic image. And also here you might be wondering of, so why are we having the options? So like, what do we do with those? Actually, there's one major use of this panchromatic band for many different sensors. So actually the reason why they give you the panchromatic band is because of the high spatial resolution, you can merge this panchromatic band with the multispectral bands to actually generate a multispectral, a color image with higher spatial resolution. So it's not possible when they record data, they won't be able to combine everything when they record data. However, once they give you the data, you have the option to merge the two different sources of information to create a color image, not black and white, but a color image, but also not in the original quartz resolution, but in a finer resolution. So by merging them together in this particular example, we can create a multispectral image with 0.8 meter resolution. And this process is known as pan sharpening. So it's just to use the panchromatic band to sharpen your image, spatially sharp. And also, actually, if you just look for the option within Erdas Imagine, Erdas Imagine, they do allow you to search. If you go to the help tab and there's a search window, you can search for different options. So if you just search for pen sharpening, there's a tool within Erdas Imagine that you can create pen sharpened image. And also this will give you some opportunity to say, you have multispectral information that you really need to use for your projects. However, you do prefer to have relatively higher spatial resolution. And then if they do give you a panchromatic band, you can combine them through pan sharpening. So, there's a reason for like sometimes why you have the option of having the different types of data. Do we have more questions? Okay, let me just go over some new assignments today. We actually have something new in addition to the lab. So for the first lab, it's due Wednesday by the end of the day. Wednesday we'll have a lab work day. So if you still need to maybe work on a few things, we can take a look at those together. And Wednesday will also be a Lab 2 workday. But in addition to Lab 2, we will have our first review assignment, which is a discussion on D2L. I'll show you quickly. And Lab 2 will be working on the second lab, image resolution. So it's not highly technical, but you'll see some basic ideas of, creating layouts, 4x4, 2x2 actually layouts and multiple image comparison, just to review the concepts of the, not the 4, but actually the 2 of these image resolutions, because they can be tricky. So let's take a look at the new review assignment. And in the meantime, let me know if you have any questions or if you have your multiple choice question.
I have a question about the projects. Should I do that later?
Yeah, let's do that later, because we haven't really talked about the projects. So yeah, so if that's if that's about this graduate project, we can probably do that during the office hours. Sean has a question. In terms of spatial resolution, fine resolution can be set to be analogous to which what other term? Coarse, high, low. So we know it should be high. Fine resolution means high resolution, and also that means the number is smaller. And Blake's question, I'll just only read the question because the option seems really long. What do the terms spectral resolution and spatial resolution signify? And let's just read the questions. I think I have my answer. Yeah, I saw some of you, I guess we're all agreeing that it should be C. Okay, nice. Let's take a look at the new review assignments. Yeah, this should be available now, and I will be sure to link to this discussion in the one-page thing. But also you can access this discussion question when you click on discussions and you scroll down. That should be here. Review assignment 1. So that is due Wednesday next week. So you will basically the same due date as Lab 2. So there are 2 parts. First of all, I want you to read this page, which is a, well, essentially the information page for Landsat 8. It shouldn't be this slow. And this page contains the information on the 4 types of image resolutions of Landsat 8. So the idea is, I wish we can take the opportunity to practice your understanding or test your understanding of the image resolutions and respond. And also, by the way, this is set to be, as you folks can see, there's a condition of release. So you have to respond first before you can see others' responses. So there's no way that you can wait and see others' answers before you post yours. So you have to post first. And if you see nothing, don't assume that no one has done it yet, because they probably have all done it. Or maybe you're the first one, let's see. So you have to respond first before you can see others' responses. And also, in addition to the information of the spectrospatial, radiometric, and temporal resolution of Landsat 8 from this page, I also want you to ask a question related to what we covered so far. And you will have to, that's kind of how the discussion assignments works. You will have to respond to at least one other's questions, or just not just only to say yes or no, but to a level just to hopefully generate some additional thoughts. I hope this works. So let's just try to get this filled out early so that you can see others' response and you can just come back and maybe respond to one another person's post. And I believe once you're here, you have to start a new thread. So you can put all your responses in the same thread, including your the 4 resolutions and also your question. And of course, by responding to another person's question, you will have to hit reply. So let me know if there are any technical questions. Okay, that's all for today. I think I'm over like 2 minutes late.